Hello, this is Mrs. Schroeder. We're going to talk about gases in this next chapter. Today we're going to talk about section 1, which talks about some characteristics of gases. We're going to cover some various objectives, describing some general properties of gases, defining pressure, and the SI unit for pressure. We're going to talk about what the kinetic molecular theory says when it talks about an ideal gas. So gases have unique properties mainly because the distance between the particles. Remember that gases are very, very far apart. They're spread, so the particles will bounce around and have a lot of space in between. Liquids and solids are close together, touching in a matrix, but gases are spread around. So gases will behave a lot like liquids, but they have a lot of unique properties. The first one is that gases are fluids, which means they can flow. The next property is their densities are much, much lower. We talk about liquids densities somewhere around 0.5 to 1.3 are kind of typical for liquids. Solids are anywhere from 0.7, things that float like cork, up to something like gold, which is around a 19. These are in grams per milliliter. Talking about gases, now we're talking about things that are 1,000 times lighter. And usually we talk about gases, densities are things like grams per liters because they're so much lighter. Gases have to travel long distances before they can collide with each other. So that changes the properties in terms of how they can be compressed and reactions that happen. They're very compressible, which means we can squish them together. And I have some demos to show you when we get to those. Gases will expand to fill the volume available. If I blow up a balloon, it expands. It doesn't just stay in one place, it fills up the entire balloon, not just staying in one side of the balloon. They'll mix readily with something called diffusion, where the particles will move around randomly and try to reach a place so that it's evenly spaced across the entire volume. A new word in this chapter is called effusion. They can escape through small holes. So diffusion is when I remove this partition, they spread around. These gas particles will spread all around here. In effusion, the partition stays in one place, but there's a little hole in the center. The gas particles can shoot through that hole through a process called effusion until they end up the same on both sides. Now, Earth's atmosphere is a mixture of gases. You guys have hopefully learned this before, nitrogen and oxygen. 70% oxygen or nitrogen, around 30%, 29% oxygen. Other things like helium, carbon dioxide, water vapor. All of those gases are less than a percentage of the atmosphere. Gravity will pull those gas molecules because gravity acts on anything that has mass. So it's pulling those molecules towards the surface of the Earth. They collide with each other. They collide with the Earth. And collisions are what is called air pressure. Anytime you have collisions, you have pressure. If I look at the atmosphere, if I started out here at sea level, you can see that the atmosphere is pretty dense. You can see a lot of particles down in this area. As I begin to climb this mountain, I'm getting less air. And if you were to climb Mount Everest, there's about 30% less air than what was at the surface. People can actually suffocate at the top of Mount Everest. They climb with bottled oxygen so that they don't die and suffocate as they climb because there's not enough oxygen for them. But again, it's gravity pulling particles down towards the Earth. And the pressure at the Earth's surface is higher, and the pressure as you climb decreases because there's fewer collisions, fewer particles to collide. Now, pressure is measured with something called the barometer, and you'll hear about that when we talk about the weather. The barometer's rising, the barometer's falling, there's a high pressure system moving in. So these all talk about the different pressures of the atmosphere as the Earth's atmosphere rolls across the surface of the Earth and up high. It creates different pressures. I'll show you a video how that works, but initially it was made with this was all mercury. And it was put in a bowl with a vacuum tube, and seeing how high that column went. That column went 760 millimeters high just from the atmospheric pressure pushing down on it. It made the mercury rise 760 millimeters. This is now a unit of measurement. We have 760 millimeters of mercury. The way you calculate pressure is it's force divided by area. So pressure equals force over area. So the SI unit of pressure is the Pascal. It's a very, very small number. Okay, pressure of a layer of water is 0.10 millimeters deep. Very, very small. So we tend to use the kilopascal more often when we measure pressure. A couple demos to do in class for you. But again, I said at sea level, we saw it was 760 millimeters of mercury. So this is one of my types of my units of measurement for pressure. These are all pressure measurements. The atmosphere is very common. 1 atmosphere is the pressure at sea level, standard atmosphere, which is what we use a lot. You may have heard of PSI also. This is in your tires. We measure things in PSI. Millimeters of mercury. Sometimes we use the Pascal or the kilopascal. Again, common units of measurement. And we'll go over some problems on how to convert pressure measurements back and forth using this chart. We'll do that tomorrow in class. And a few more demos to show you some of these properties. And that's about it for now.